So hello everyone, my name is Mohammad Refat, and I'll be talking about star spot inference using light curve inversion techniques. And my thesis advisor was Lucy Liu at Ohio State University. So first, I'd like to start by talking about sunspots. So sunspots are just dim patches on the sun that are a result of magnetic activity. And the image here you're seeing is our Earth on the surface of the sun, just for scale purposes. So this is kind of what it would look like on our sun. So a star spot would be the star analog to a sunspot. So kind of the same idea. They're also formed by magnetic activity, and we want to study these because it gives us an insight into the magnetic activity of stars, which helps us understand them more. But it also can help us understand stellar structure and evolution. So I will begin now by talking about light curve inversion. So light curve inversion is a tool that attempts to recreate a star's surface from a light curve. So the advantage of this is that all it requires is a light curve, which is pretty easy, relatively easy to obtain. It's easier to get than directly imaging the surface of a star. So this is really good because we have a lot of light curve data, so we can use it on that. And we also obtain a lot of light curve data in the future, so we can do this with all of that. However, the issue with this process is that it's highly degenerate, so we don't know what information from it is correct. And if you can think about it, you're just taking flux and time and trying to convert it into 3D space. So we're not going to know for sure what the surface looks like just from this. So kind of one of my goal here is to find any kind of trustworthy information from this process. So in this image, you're seeing light conversion. So on the top here in red is the fit created by light curve inversion, and then the little dots are the original light curve. And then on the bottom, you're seeing what it thinks the surface of this star looks like. So these dark patches here are the two star spots that are assumed from this light curve. So as you can see, as you can rotate the star, that's what it looks like. So there are different methods of doing light curve inversion, and this one is specifically tailored for star spots, and I'll talk about one right now. So the first method I will talk about is a package called Starry. So this package uses spherical harmonics to calculate its light curve inversion. And spherical harmonics are just functions we use when we want to work with spheres. So here on the y-axis, we have L, which we call the degree, and M is the order. So within a degree, you add up all these spheres, and you get the surface of your object. So if you look at here, which is L equals 1 and M equals 1, as it rotates, the flux of the light curve will change. So as it gets to the more purple part, the light curve will dim. But if you look at over here, which is M equals -1, as it rotates, you don't really notice a change. So that's kind of how this works. So this is one of the packages that I used. So this is it in action on Earth. So on the right, you're seeing the different shades are like how much weight each of the harmonics has. And when you add them together, you get the surface of the object you're looking at. So on the left is the result of this. So you can see if we have an L of 5, it's pretty blurry and you can't really make out the continents of Earth. But if you go as far as L equals 20, you get a much better picture of Earth, and you can see what's actually going on. The only kind of issue is a higher L allows for more complex calculations, but it also takes more time. So that's something to take into account. And then another package I want to talk about is Flex. So this is one designed more specifically to deal with star spots. And so on the right, you're seeing what it thinks the surface is, and there are 3 star spots here. So this is done on a real star, V1298 tau, and there's 2 plots it comes up with on the left. So this one here is showing the light curve. The black part is the original light curve, and then the blue is the fit that it produces. And then the second plot here is what's called the star spot filling fraction. So that's how much of the surface of a star is covered by a spot. So this next package I want to talk about isn't a light curve inversion package, but it is very important to what I was doing. So it's called Butterpie. So what it does is it simulates stars with evolving star spots. So in this animation here, you can see this is a rotating star over time, and these little circles here are star spots that are changing in size. So as you can see, as one comes into view, the flux of the light curve dips down, and when it goes out of view, it goes back up. So on the right, you're seeing 5 light curves from the sample I was given to work with. And with this package, we use this package because we'll know for sure what the light curve is and what the surface looks like. And I've tried this on physical real stars before, but the issue is due to observation limitations, the light curves you get aren't full, and the results come out kind of weird. So in this sample, I have 1,000 light curves that I used. So, and on the right, you're seeing just 5 of them. So for the first comparison, here is all the packaged together and their fits. So in the yellow, we have the original light curve from Butterpie. One thing to note is that over time, the amplitude is changing, whereas with the other 2 packages, no matter what over time, it likes to keep the same amplitude. And one parameter we put into both these packages are periods, so that's why you can see that over time, the period stays the same, and it repeats pretty well. So within this specific light curve, in the red, you can see it likes to fluctuate a little more, versus Starry, where it likes to keep less peaks. So this is one of the things I did. So next, I'm showing the distribution of spherical harmonics versus activity level. So except for Y00, you can see for the most part, there's a trend for the activity level to increase along with the spherical harmonic. So we think this is due to the correlation between flux and activity level. So we also have other parameters to compare this to. So here is a comparison of flux and activity level. So as you can see here, again, this is why we think there's a link between flux and activity level. So as it increases, so does activity level. So this is kind of one thing we see. So in conclusion, we want to study star spots using light curve inversion and learn what information we can get from it. We use Butterpie as a comparison point, and then we use these 2 packages to compare these tools. So we potentially see a link between activity level and spherical harmonic degree. And in the future, I would like to do this, or anyone else who will maybe want to work on this, use real data. So before I finish, I'd like to thank a lot of people. So first, I'd like to thank Lucy for working with me throughout my entire master's degree. I'd like to thank Ali and Jillian, especially Ali. I've known her for such a long time. I'd like to also thank the rest of CUNY Astro. I'd like to thank the Science Foundation. I'd also like to thank the CUNY Masters Cohorts 1 through 3. And I'd like to thank you all for listening.
Great talk, Mohammad. Really cool to see after all these years of work, a lot of these things coming to fruition. You quantify activity level. How so? What's that based on?
Oh, that is a given parameter of the stars that we have, the catalog of stars we have.
Oh, okay.
Yeah.
Is it readily trackable to number of spots or size of spots or magnetic field, or is it just something else, sort of?
So I can't tell you for an actual star what that would be like, but for the stars we were given, they were just generated with a bunch of randomly set parameters, and that was one of them. So that's kind of the input. And
it's a knob you get to turn. Okay, good. Thanks.
One of the animations you had, it showed the star spots growing and shrinking. This one. What physical thing is happening that would cause a star spot to shrink and grow? Is it like fluctuations in the magnetic field, or what would happen physically to?
Yeah, change in magnetic activity.
Okay. Thank you.
So great work. How far are we from seeing continents on exoplanets?
I can't tell you. I think we'd really need I think we'd need a really, really good, clear light curve of a planet. I'm not actually sure. That'd be interesting to think about. Yeah, I'm not thinking about real stars yet. That's where this started, but then didn't go too well. Yeah.